Welcome to the Science of Emotions podcast with Ruben Singh, MD. This is your host, Ruben Singh. In this episode, we're going to discuss a review article by Kenneth Davis and Christian Montag. This article is about Jaak Panksepp's affective neuroscience. He's the pioneer of affective neuroscience. In the early 90s of the 20th century, Jaak Panksepp coined the term affective neuroscience, today being accepted as a unique research area in cross species brain science. By means of electrical stimulation, pharmacological challenges, and the brain lesions of vertebrate brain, mostly mammalian, Panksepp carved out seven primary emotional systems called seeking, care, play, and lust on the positive side, whereas fear, sadness, and anger belong to the negative affects. Abundant research into human clinical applications has supported the hypothesis that imbalances in these ancient primary emotional systems are strongly linked to psychiatric disorders such as depression. This paper gives us a concise overview of Panksepp's main ideas. It gives an historical overview of development of Panksepp's affective neuroscience thinking. It touches not only on areas of neuroscience, but also shows how affective neuroscience has been applied to other research fields such as personality psychology. Finally, the present work gives a brief overview of the main idea of the affective neuroscience. A brief introduction to the Jaak Panksepp's scientific career. The scientist who coined the term affective neuroscience, Panksepp, had the insight as a young clinical psychology student working in a mental hospital that understanding emotions was a key to developing more effective treatments for psychiatric hospital patients and all those suffering from psychopathology. This insight led to his graduate school career change from clinical psychology into what now we call neuroscience. He also realized that level of understanding that we needed would require brain research that could not be conducted on human beings. Hence, he began and probing the neural constitution of emotions and the deep foundations of mammalian brain. In his dissertation, he was able to use electrical stimulation of brain, that is ESB, to elicit two distinct emotional affective behaviors in rats. First, affective attack towards another rat, and a predatory, quiet bite attacking a mouse. He was further able to show that these rats subjectively experience these two contrasting emotions, meaning they would work to turn off the stimulus eliciting the affective rage attack, but would work to turn on and receive more of the stimulus eliciting the quiet bite, which was later shown to be activating the seeking system. In wake of the discovery in early 1970s of endogenous opioids in the mouse brain, Panksepp began working on another potential emotional behavior system in the brain. J.P. Scott, a senior colleague at Bowling Green State University, had studied the social behavior of dogs for many years and was exploring the separation distress vocalizations in puppies. Meanwhile, Jaak had recognized the similarities between opioid withdrawal in drug addicts and the social distress caused by broken relationships, and had also noticed that opioid addicts frequently came from marginal family social backgrounds. Panksepp hypothesized that opioids might be related to mammalian separation distress calls. And at BGSU, that's Bowling Green State University research group, soon demonstrated that low dosages of morphine would soothe the separation distress vocalization in canine puppies. In 1980, after his lab had successfully mapped distress vocalization sites in guinea pig brain, Panksepp went on to publish his opioid hypothesis, namely that brain opioid likely underlie the formation of social attachment and modulate the social emotions and behavior. By 1982, Panksepp had convinced that there were at least four biological brain systems that were based primarily on emotional action systems, which at that time he labeled as expectancy, rage, fear, and panic. In a psychological review paper in 1992, and especially with the publication of book Affective Neuroscience, Panksepp had expanded his list of primary emotions to seven well-documented primary process emotional command systems. Those are seeking slash expectancy, rage slash anger, fear slash anxiety, lust, care slash nurturing, panic slash sadness, and play slash social joy. And Panksepp introduced the use of capitalization to distinguish these primary emotional brain system from the use of his chosen emotional labels in common language. The mapping of the seven primary emotional system by means of electrical stimulation of a mammalian brain, including pharmacological challenges and brain lesions, represents the heart of what Panksepp named affective neuroscience. Of note, Panksepp concluded that there was insufficient evidence to include social dominance as a primary emotion, and he considered it as acquired behavior. Panksepp did include a detailed treatment of the homeostatic affect hunger in affective neuroscience book, but did not consider it in the same category as emotional affects, which were directly relevant to mammalian psychopathology and personality. In the next segment, we talk about the mammalian brain and mammalian affective systems. Mammals are deeply affective. All mammals are sentient beings, meaning that it feels like something to be alive and dealing with the challenges in their worlds. The philosopher Langer, in her book, Mind, an Essay on Human Feelings, writes, quote, "To feel is to do something," unquote. The word emotion is derived from the Latin verb emovere, meaning, quote, "to move out." And that seems to be what we observe already in the evolution of early life. Primal emotions and their accompanying affect appears to have acquired the capacity to move animals to action in ways that promoted their survival. Emotions prodded animals to explore for resources, that is, seeking, compete for and defend for those resources, that is, rage, escape from and avoid bodily danger, that's fear, identify potential mates, and reproduce, that's lust. Then mammals with their more social orientations acquired the motivational system for nurturing their offsprings, that's care. The powerful separation distress system for maintaining social contact and social bonding, that is panic and sadness. and the complex system stimulating especially young animals to regularly engage in physical activities like wrestling, running, chasing each other. That is play slash social joy, which helps them bond socially and learn social skills and social limits, which seem to carry over into the quote unquote ribbing and joking that continues to add fun in adulthood. Evolution has endowed mammalian brain with at least these seven primary process emotional action systems, which serve as survival guides. These primary emotions arise from subcortical brain regions that are largely homologous, especially across mammals, with each emotion having a distinct brain anatomy, neuropharmacology, and physiology. Jaak Panksepp felt that the key affective neuroscience question was the neural constitution of raw affects, which was essential for understanding our own affects and for developing better psychiatric treatments for emotional imbalances, but which would require further causal preclinical research into our ancestral subcortical primary process emotional brain systems. Mother Nature, also known as evolution, speaks to all mammals in oldest language, the language of emotional affects. Each of the primal emotional affects is evaluative. That is, there's a valence that is either pleasant or aversive and signals the objects or situations to approach in case of pleasant ones, that is, seeking, lust, care, and play, or to avoid in case of aversive ones, rage, fear, and panic. Yet, experiencing a primary affect does not necessarily mean all mammals can self reflect on their emotional experiences. That capacity may be reserved for more cortically endowed mammals. However, the raw primary affects are experienced as pleasant or aversive qualia, which alter the behavior and provide for secondary level learning. That is the conditioning principles. The emotional minds of most mammals may be limited to displaying intention in action rather than more reflective intention to act. In Andel Tolwing's terminology, capacity of most mammals likely combine anoetic, that is without knowing, and noetic, that's knowing consciousness, without necessarily attaining autonoetic consciousness, that is, being able to sufficiently hold experience in memory to review the past and anticipate the future. We know that animals experience primary affects because of the empirical measures. They will work vigorously to sustain affective states by learning to turn on electrical stimulation of brain evoking positively valenced emotions and correspondingly escape or avoid the negatively valenced emotions. They will also demonstrate conditioned place preferences or aversion for situations where they had experienced such stimulation in the past. Further, animals will limit conditioned positive and negative vocalization in places where they have experienced positively or negatively valence ESB. However, we are unable to measure feelings, that is affective qualia, directly, not even in humans. Apart from experiencing primary process emotional affects, what is much more difficult to study in non-human mammalian world is Tolwing's autonoetic consciousness, characterized by capacity of humans to experience affective nuances, often reflecting human higher order cognition and language, including having thoughts about thoughts. This represents a limitation of cross species affective neuroscience. However, subtler models of affective concepts such as pessimism in dogs, optimism in rats, and regret in rats are appearing in cross species studies. Now, the next section is about the learning and the memory system related to primordial emotions. Primordial emotions are innate but are also adaptive learning and memory systems. Primary process emotions require no learning. It is not necessary to teach a child to become angry, fearful, or to panic after having lost sight of a parents in a crowd, nor do we need to teach children how to play. These evolved foundational tools for living are somehow automatically built into our heritage. However, these evolutionarily genetically endowed primary process emotional brain systems are not fixed functions but are able to learn and adapt to novel environmental experiences throughout the life of an individual. Indeed, as introduced above, the valence affects associated with each of the primary emotions serves as endogenous reward and punishment for behaviors that activate emotions. For example, receiving painful stings from hornets flying out of the nest you accidentally disturbed fills you with fear. And without thinking about it, you immediately react by running away from the menace. Having reached a safe distance, you feel relief that you seem to be out of danger and likely begin to examine your tiny wounds, which are beginning to swell slightly as the pain intensifies. And you may begin to clarify at a safe distance the details of Hornet's nest's appearance and location. This event will be forever embedded in your memory, and you will have learned to avoid repeating this experience by remaining more vigilant when outdoors walking through unfamiliar terrain. The primary process emotional command system likely encompass a separate reward or punishment system. These learning systems can be thought of as a secondary process integrating new experiences into primary framework, allowing for previously neutral environmental stimuli to elicit the emotions and for novel reaction to become associated with each stimuli. For an example of novel reaction to an emotional arousal over the ages, humans, when threatened, have learned to reach for their swords and recently their pistols instead of clenching their fists. However, more evidence is needed regarding the extent to which these different emotional systems encompass different learning and memory parameters. While the deep brain stimulation allows researchers to demonstrate that brain stimulation at the specific sites evokes distinct emotional behavior that are accompanied by corresponding affects, there remains to be a question of whether the emotional affects elicited at these sites are primarily distinct. We do know that rats can learn to discriminate between deep brain stimulation in the hypothalamus and septal region of the brain. We also know that animals can distinguish between emotional states induced by addictive drugs, morphine, and cocaine. We also know that deep brain stimulation in humans at homologous brain sites seem to evoke homologous affects. However, much more research needs to be done before there is any clear assurance regarding the number of distinct primary affects or role of electrical or pharmacological stimulation in generating these affects. Now, these primary process emotions survive decortication. Primary affects are constituted at the subcortical level. That is true for primary emotional affects such as anger, fear, or homeostatic affects such as hunger, thirst. There is ample evidence that primary process emotional brain systems do not require the neocortex. In rats, decortication does not block the rewarding effects of subcortical electrical stimulation of brain. That's ESB. In humans, strong emotions decrease cortical activation, and the cortical damage often lead to increased emotionality, which is consistent with the cortex generally providing the inhibition and regulation of emotions rather than activation. Further support in humans for subcortical emotions without the cortex is offered by Merker, who has reviewed the case of hydranencephalic children who are born without a cerebral cortex. He writes that even without a cerebral cortex, these children express pleasure by smiling and laughter, and aversion by fussing, arching of the back, and crying. Their faces begin being animated by these emotional states. He further comments that their emotional behaviors are accompanied by situationally appropriate signs of pleasure or excitement on the part of the child. These children clearly show that appropriate emotional responses, even in humans, do not require the participation of the neocortex, as further evidence of an independent subcortical brain that can function without a neocortex. Merker also reviewed Penfield and Jasper's paper in which brain surgery under local anesthesia was performed on conscious patient with a history of severe epileptic seizures. These surgeons removed sizable sections of the cortical tissues while communicating with the patient, which never interrupted the patient's continuity of consciousness even while the tissue was being removed. Along these lines, Damasio et al. Reported the case of patient B, who had contracted herpes simplex type 1 encephalitis, that's HSE, which had destroyed much of his cortical brain tissue with extensive bilateral cortical damage, including the temporal lobe, temporal pole cortices, orbitofrontal cortices, and anterior cingulate cortices. Plus, the left and the right insular cortices were entirely destroyed, as well as the bilateral entorhinal cortex, hippocampus proper, and amygdala. In short, patient B had lost structures thought by many to be integral to emotional experiences: the insula, amygdala, the anterior cingulate cortex. Yet all indications, including the observation by strangers, observation of the research team, psychological evaluations, and a structured questionnaire completed by his spouse comparing his emotional behavior before and after his disease, were that patient B retained a full range of appropriate emotions after his brain disease. The lack of importance of cortex for emotional behavior and displays was supported by Winslow's 1990 review of experimental rat decortication literature. While there were differences between whether the surgery took place neonatally or close to maturity, the neonatal group showed few deficits. With neonatally decorticated rats, loss of cortex essentially did not disrupt survival, emotional behaviors, and displays. These subjects exhibited no interruption in post surgery sucking and grew to maturity with near normal heights and weights. They exhibited normal posture during face washing with no deficits in grooming. They were also able to reproduce, with 6 out of 8 females being able to successfully raise their litters with normal cleaning, suckling, and caring for their pups. As juveniles, they played as much as controls, and most components of aggressive and defensive behavior were present, including lateral displays in response to an intruder, and conditioned freezing after having been attacked, and later being reintroduced as an intruder to the same cage with the same resident. The theme of the small subcortical lesions having dramatic influence on emotional behaviors, such as losing virtually all spontaneous activity after ablating periaqueductal gray, was convincingly addressed by Fernandez and Hunsberger in 1962. They showed that rage responses of cats could be evoked by ESP along the basic subcortical mammalian rage system running from the periaqueductal gray at the lowest level up to the medial hypothalamus and on up to the medial amygdala at the highest level in the decreasing level of importance. As such, they found that aggressive responses evoked by ESB of the amygdala were abolished by lesions at the level of hypothalamus or PAG. Aggressive responses from hypothalamus were dependent on PAG but not on amygdala. And at the lowest level, aggressive responses evoked by PAG level were not dependent on either of the higher two levels. Further field studies with cats receiving small lesions to what they call the hissing zone of the PAG when confronted with a dog no longer hissed or attacked. So based on these studies, clearly our primary process emotions and their powerful affective message are deeply embedded in our mammalian brains. Humans and other mammals still experience these emotions without a neocortex, and the subcortical regions are organized in an evolutionarily hierarchy of importance. Understanding of these cross-species emotional system may represent the greatest challenge to neuroscience. Again, in the words of Jaak Panksepp, quote, for affect neuroscience, the key question is the neural constitution of raw emotional homeostatic and sensory affects. Unquote. Another PET study provided evidence from blind subjects for the use of visual cortex for auditory processing. Weeks et al. Used PET to determine which subcortical areas were being activated during auditory localization tasks. While sighted and blind subjects both showed activity in the posterior parietal cortex, only blind subjects also showed activity in the occipital cortex, a cortical area that is normally associated with visual processing. Thus, cortical plasticity seems to allow blind individuals to develop enhanced tactile and auditory capabilities by redirecting the neocortical regions typically thought of as visual processing regions to enhance other sensory functions. Experimental research from MIT research group supported the reprogramming finding documented in blind subjects. Using ferrets, a species born in an exceptionally immature stage, visual inputs were surgically redirected to the auditory cortex shortly after being born. And as predicted, auditory cortex was developmentally programmed to process vision. A follow-up study using similar procedures with mice showed that rewired mice could learn visually cued conditioned fear. Both set of animals with visual input redirected to auditory cortex developed fine cortical visual abilities, even though their neocortical processing was developmentally constructed rather than genetically dictated. The idea that we should not expect to find evolved specialization in neocortex was further supported by the report in Science that a single gene called ARHGAP11B, that is ARHGAP11B, was responsible for much of the massive expansion of the human neocortex. The researchers further determined that this newly identified gene was found only in humans, Neanderthals, and Denisovans, another extinct hominid line in southern Siberia. The gene was not found in our closest living evolutionary relatives, chimpanzees. This finding makes it increasingly unlikely that any of our neocortical higher mental abilities present evolutionary genetically determined specialization like those that are found in the subcortical brain region. The neocortex is likely organized by subcortical function of the brain. The idea that subcortical brain systems guide the development of cortical specialization gained support from Panksepp's group investigating the possible role of play in development of frontal cortex. Working on the evidence that right hemisphere frontal lobe deficits were associated with ADHD, that is, attention deficit hyperactivity disorder, and the knowledge that the symptoms of frontal lobe damage generally resemble ADHD. It was hypothesized that right frontal lobe damage might be a useful rodent model of ADHD. They found that right frontal lobe lesions in rats performed at 3 or 4 days of age significantly increased playfulness, as well as increasing activity levels, confirming the hypothesis. Activity level of both sham and lesion animals decrease with age. However, in rat pups with frontal lesions, 1 hour per day of play therapy for 7 consecutive days, tested at 30 days of age, significantly reduced the number of pins and overall activities, ameliorating the elevated play urges and activity levels. Indeed, the play therapy even significantly reduced overall activity in the sham lesions control subjects. Another line of research proposing that innate subcortical system guide the development of refined neocortical capacities come from the work of Mark Johnson's group linking the infant's facial preferences to adult face recognition and related capacities. Now, these two research lines illustrate that basic subcortical processes likely constitute primary process experiences that become developmentally elaborated in neocortex. With maturation, these physically as well as evolutionarily separate brain regions develop a reciprocal seesaw like relationship to weigh whether a life event should trigger or inhibit expression of primary emotions, with imbalances in either direction potentially becoming dysfunctional. It has been reported that more ancient cortical midline structures, such as ventral medial prefrontal cortex, may participate in such reciprocal relationships with more cognitive brain regions such as lateral and dorsal prefrontal cortex. However, despite increasing cortical influence with maturation, it remains clear that subcortical emotional system retain the capacity to shut down the cortical activity during strong emotional experiences. Along these lines, there is evidence that all long-term memory has emotional component. With stronger emotions, the resulting memory becomes correspondingly stronger, with the exception that traumatic emotional experiences can reduce the memory retrieval and even cause amnesia. Typically, stronger emotional activation is associated with stronger memory retrieval. With strong positive emotional experiences such as wedding and strong negative emotional experience such as the funeral of a loved one, both enhancing memory strength. Moreover, one of the basic functions of the primary process emotional memory system may be arousal and drawing attention to specific events that can facilitate the formation of memories for important life events that in turn can subsequently inform how we respond to future life events. With ongoing guided acquisition of experience, the neocortex surely provides many refinements and expansions of our basic subcortical capabilities, with the caveat that an ever vigilant subcortical brain can assert its predominance in response to genetically linked wisdom embodied in, that is, pent up urges to play or fear endangered by menacing face of a predator. Hence, if an evolutionarily significant cue resonates in the primary emotional system, the subcortical energy can override our activity in the cortical thinking cap. This developed two-way, that is bottom-up and top-down relationship requires the ongoing involvement of our affective states, influencing our perceptions, thoughts, and urges, as well as the acquired cortical capacity to modulate our emotional evolutionary foundation in order to achieve an appropriate seesaw positioning for ongoing life events. Yet much of the research remains to be done to eliminate the mechanism involved in these evolutionarily integrated processes. the route to discovering primary process emotion. At least since ancient Greeks first speculated about four humors and Ptolemy proposed the sun, moon, planets set our behaviors and emotions, humans have speculated about the basis of personality and psychopathology. More modern theories have ranged from Freud's theory of sex and aggression on personality development to the thesis that differences in our personality are mostly learned. Cattell pioneered using lexical hypothesis, the assumption that any important human characteristics were embedded in language, and the factor analysis and the first reported four personality factors by Cattell in 1933. But an increasing computing power allowed for working with larger data sets, as he eventually proposed as many as 19 distinct factors, with 16 being used in the most widely used personality assessment, the 16 personality factors. That was by Cattell in 1970. However, others using factor analysis reported as few as 3 and as many as 20 personality dimensions. Many others took up Cattell's approach, considering factor analysis as a more theory free and objective statistical approach to parsing personality into its components, an approach that may have peaked in accepting five personality dimensions. The big five were massively shored up by Lewis Goldberg's seemingly exhaustive factor analytic studies, as well as a report confirming that these five personality dimensions plus dominance in chimpanzees. The big five scales are typically labeled extroversion, agreeableness, conscientiousness, emotional stability, and openness to experience. Even the psychiatric world got on the Big Five bandwagon, identifying dysfunctional dimensions consistent with the Big Five scales. However, the lexical Big Five personality bastion now seems to have splintered into multiple competing theories, proposing six and even seven personality dimensions, and even theories with only one, two, or three dimensions. Agreement on parsing the human personality have been very difficult to achieve. Panksepp took a different approach to carving nature at its joints by using electrical stimulation to directly probe the brain for its secrets. He followed in the tradition of Hess, who in 1930s had evoked a cat rage response using electrical stimulation of brain, that's ESB. The basic idea is that if experimenter introduced a crude, unstructured electrical stimulus into a particular brain region and reliably evoked a consistent, coherent emotional action pattern in the subjective affect state that can be verified to be pleasant or aversive using self stimulation or approach avoidance measure in animals, the ESP has activated an innate, unconditioned, evolutionarily organized brain circuit linked to the observed emotional behavior. Mainly using ESB, but also pharmacological manipulation and localized brain lesions, Panksepp identified seven emotional brain systems as listed: seeking, rage, fear, lust, care, panic, and play. These ESP sites are concentrated in subcortical region of the brain and correspond with Panksepp's primary process emotional action command system. Cases of such dramatic and unambiguous emotional behavior or affects have not been elicited from the neocortex. However, more muted displays of laughter have been reported from evolutionarily more ancient cortical areas such as anterior cingulate cortex, which is consistent with the finding that the most striking coherent results with the lowest stimulation required are obtained from evolutionarily ancient subcortical regions as periaqueductal gray, that's PAG. primary process emotions and the foundations of personality and psychopathology. One of the ways to verify and extend the validity of a theory is to make predictions and determine whether the evidence confirms the theory. One of Panksepp's prediction was that primary process emotions provided the psychobiological foundations of personality. To begin linking the primary emotions to human personality, affective neuroscience personality scales, that's ANPS, was developed. ANPS was designed to measure self reported activity of six primary emotions in human lives: seeking, rage, fear, care, panic, and play. Lust was excluded as it might limit valid responding and elicit highly socially desirable response patterns. ANPS has been translated and validated in 10 different languages. In comparison of the ANPS and Big Five and five factor model personality assessment has uniformly shown close association of six emotions to these personality measures. While ANPS play consistently lines up with Big Five extroversion and seeking with openness to experience, it is also clear that from these studies that some five factor personality scales are higher order configuration of more elemental primary process emotions. For example, the Big Five factor model agreeableness scale combines the care system, which is associated with the high level of agreeableness, and rage system associated with low level of agreeableness to conceptually create a love hate scale. Further, the Big Five five factor model emotional stability scale places all three of negative valence emotions, that is, rage, fear, and panic, on a low end of emotional stability, making emotional stability a confusing scale to interpret, but also conflating the distinction between these problematic emotions that are so closely linked to the etiology and treatment of psychopathology. These associations are stable across cultures, and same patterns between individual differences in primary emotion systems are assessed with the ANPS and the Big Five personality have been observed in many countries, including studies in USA, Germany, China, and potentially hinting at a global ancestral neurobiological effect. Thus, while much work remains to be done linking the primary process emotions to more tertiary language derived personality models, initial evidence is that there are close associations between Panksepp's primary process emotional action systems and standard Big Five personality assessment, with the caveat that primary emotions offer a more direct psychological personality view that more clearly eliminates each of the foundational elements likely constituting our personalities. An additional note is that no consistent association has been observed in these ANPS studies between ANPS measured primary emotions and the Big Five conscientiousness scale. The thought is that conscientiousness does not measure primary process emotions. Rather, it likely measures some aspect of neocortical inhibition and the resulting cognitive regulation of the primary emotions, thus providing tertiary process top down control over subcortical emotional reactions. It has long been thought that psychopathology represents the extreme expression of personality characteristics, and that personality disorders and other psychopathologies can be classified on the Big Five five factor model dimensions. Along these lines, ANPS studies have shown that Panksepp's primal emotions can be used to differentiate between bipolar 1 and bipolar 2 disorders, as well as personality disorders. Panksepp also made several additional predictions about the psychiatric treatments that have been tested. Panksepp predicted that autistic children might have dysfunctional brain opioid systems resulting in excess endogenous opioid levels. Experimental research has supported this proposal that autism could potentially be treated with low dose naltrexone, that is, an opioid blocker, and suggests that naltrexone benefited a subset of children diagnosed as autistic, with as many as 40% of autistic children exhibiting enhance social integration when treated with naltrexone therapy. So, next we summarize the main key points from Jack Panksepp's career and affective neuroscience. Jack Panksepp's career spanned 50 years. Throughout, he worked on to provide compelling evidence that animals experience their emotional arousals, at least all mammals, probably all vertebrates, and with the likelihood that even some invertebrates, such as crayfish, exhibited conditioned preferences to distinct visual environments when associated with injected addictive drugs abused by humans, such as amphetamines. His was an evolutionary approach that confirmed Darwin's continuity thesis that humans are also animals. He became increasingly committed to the principle that this cross species affective neuroscience approach would provide the foundational understanding of our subcortical primary process emotional affective nature that would be necessary for understanding the neocortical tertiary level blending of the primary and secondary process values with the neocortical analysis and linguistically based interpretations of the experience. Further, animal models taking advantage of evolutionarily conserved brain homologies would facilitate the development of novel psychiatric treatments of human emotional imbalances. Yet, a more cognitively neuroscience focused climate convinced that subjective feelings were largely restricted to humans, produced cortical fMRI images of emotional manifestations in humans as their evidence. Panksepp frequently found himself writing that fMRI technology using measures of brain blood flow and oxygenations were better suited to analyzing the large networks of rapidly firing neurocortical cells engaged in cognitive information processing than physically smaller regions of slower firing subcortical neurons associated with unconditional emotional behaviors and their affects. The more difficult PET imaging seemed to be better choice for eliminating subcortical processes. However, there have been exceptions with the well-designed fMRI studies working with strong emotional arousals, highlighting the importance of subcortical structures like PAG. Yet there remains an unresolved debate in the neuroscience community. A major difference reflects Panksepp's position that subcortical activation is sufficient to generate emotions and their affective states that are reviewed above in section primary process emotional survive decortication. The cognitive neuroscience counters the position that emotional experience is a quote unquote readout of emotional bodily reactions, which means that cortical perception are also necessary. A related dispute emerged from the idea that emotions are learned and quote unquote constructed by elaborated from pleasure and displeasure, arousal, dimensions by multiple regions of the brain. Whereas Panksepp is clear that primary emotions require no learning and are generated by genetically defined subcortical brain circuits. Yet Panksepp was eager to reunify emotion theories at the end of his career. Among others, Montag and Panksepp provided an overview of how Ekman's facial expressions, that is, the view of emotions from the outside, were linked to affective neuroscience, that is, the view of emotions from inside. Beyond this, he also, as a response to constructivism in emotion theories, he wrote, quote, a primary process basic emotion view may prevail in many subcortical regions, and the constructivist dimensional approach may effectively parse higher emotional concepts as processed by neocortex. In other words, such debates may simply reflect investigators working at different levels of control. Whatever the future of affective neuroscience in contributing to our understanding of human mind, from its creative heights to its distressing imbalances, it is heartening that frontiers of research and affective neuroscience continue to explore these areas. In further episodes of The Science of Emotions, we'll discuss these 7 basic emotion systems by Panksepp in more detail, each separate episode for each basic emotion system. So that concludes our review of this article for Affective Neuroscience Theories of Jaak Panksepp. I hope you enjoyed this episode and see you next time. Thank you.